So we're going to be covering, basically, it's a method-oriented class, right? So we are not really going to be talking about any specific applications, but we are going to be covering different methods that actually each of them has are suitable for different applications, but each of them are suitable for more than one single application. We are covering finite difference, finite volume, finite element, and boundary element methods. So after these 4 methods, we are also going to be discussing topics that is applicable for all, for many, if not all of these methods, like direct and iterative solution methods. These are methods for solving large-scale linear and nonlinear equations. That is usually a result of using one of these methods to convert a partial differential equation into a finite set of equations. I mean, the way I see it is that a partial differential equation is actually an infinite set of equations. An equation that it's satisfied at every point in space and also potentially every single time. And space and time are continuous, right? So there are infinite many points you can choose and infinitely many time instances you can choose. And so the equations are actually an infinite set of equations. If you use any of these methods, you are going to be reducing or approximating this partial differential equation with a finite set of equations. Although finite, the equations may be extremely numerous. It's not uncommon to see the number of equations on the order of billions. Okay, so if you have a billion, not just the independent, but also coupled equations, which means you cannot solve one and then another, right? You have to solve the billion equations simultaneously. And the direct and iterative solution methods are methods of solving a huge array of interdependent equations simultaneously. Also, we are going to be looking at error analysis and sensitivity analysis. So error analysis really is about how much error are you introducing through this approximation. So because we reduced the infinite set of equations to a finite set of equations, as of now, there is no way to perform that approximation in a general and exact way, right? So you are going to be, all of these methods we are going to be talking about is very generally applicable, but all of them makes approximations, right? I mean, that's actually the difference between analytical and the numerical method. If you have an analytical method, you make no approximation. But up to now, especially for partial differential equation, there is no analytical method that are general. Actually, my study is in mathematics and like pure mathematics in my undergrad. And the class partial differential equation is the most disappointing class I took in my undergrad. I mean, the reason is in pure mathematics, the class they teach in pure mathematics are not numerical. They are doing exact analytical methods. And you can actually do a lot in ordinary differential equations, right? You can prove a lot of things and in ordinary differential equations. So the next class, partial differential equations, I came with high expectation. And at the result, at the end of the class, I learned so little that I thought this is the lowest class in terms of value divided by expectation. And that's actually one of my primary motivations of going into computational mathematics in my graduate study. So that's using numerical methods that can generally solve equations, but the cost is now you have to make approximations. And error analysis basically figures out, now I have made that approximation, how much error is there in the end result. So how much error is there between my numerical solution and that hypothetical analytical solution that I have no way to find out. So that's error analysis. Sensitivity analysis is related in its method, but very different in its application. So sensitivity analysis is about if I change the input of the partial differential equation a little bit, how much does that affect my output? And usually a partial differential equation involves a huge number of inputs. For example, if I'm solving the partial differential equation that describe the behavior of an airplane, the entire geometry of the airplane, how its wing is shaped, how big is its fuselage, right? What's the shape of its landing gear, etc., are the inputs to this solution of the partial differential equation. So if I can do sensitivity analysis, I can figure out if I change these things slightly, how would that affect the end result, which may describe how efficiently the aircraft may perform or how safe the airplane is. Okay, and that is going to guide the designer of the airplane to say, okay, I should make this part of the wing thicker, I should make the landing gear a little bit tweaked towards the outside, etc. Right? To, for example, increase the fuel efficiency, which reduces emission, or reduces the potential vibration you have when the pilot put down the landing gear. All right. So this is the 4 methods of solving differential equations and something that is more generally applicable. That's going to be covered in this class. So good news is that there is no exams in this class and no problem sets. And but this does not necessarily mean it's good news. That means like all the work expected in this class are in the projects. So expect a lot of coding and debugging, and the prerequisites are you have to really know your linear algebra very well. And we also expect knowledge about ordinary differential equations. All right. So previously we have been using MATLAB to do all our homework. But over the past few years, I see more and more demand of moving to other languages, like Python. How many of you are more familiar with MATLAB than Python, and vice versa? Can I get a vote of those who prefer MATLAB to be still used as the primary language? And how about Python? Okay. So it looks like still MATLAB is the main thing people want to use. So let's just stick with it. So I'll basically be using MATLAB as the primary instruction language. Okay, and so the self-assessment project, because actually last year I got more Pythonists than people who want to use MATLAB. So the self-assessment project, I made it to be more like a Python friendly. But let's actually allow both for this semester. So you can either use MATLAB or Python. All right. So the self-assessment project, it's 0%, but I think it's a good way to kind of for you to get a feedback of how your background, especially programming type of background, is like. Is it suitable for starting this class? I made it look like it's Python, but you can also do it in MATLAB. And the rest of the projects that actually counts are 4 projects, one with each method, right? Finite difference, finite volume, finite element, and boundary element method. At the end of the class, you are supposed to design your own project that counts 28%. So for those who already have a research interest, it's a good bargain for you, because you can do a project that can help both, that can both show to your advisor and show to me, right? So for those who don't have a research project yet, you can figure out whatever you are interested in and do something relevant to this class and to what you're interested in. And I think it's usually the last class is basically for everybody to present their own project. It's a very short 5-minute presentation. But it's usually very satisfying for me to see all the applications of what I taught that I never imagined, and potentially for you to know a little bit more about how other people can apply numerical solution of PDE to other things. All right. So questions about the how the class is going to be? No? Are you sure to get some questions? Yes?
On projects, we can code them in whatever we want to, whatever language we want, or should we do, are we required to do that?
You don't have to ask me if you code it in Python or MATLAB. If you want to code it in some other language, please seek my approval first.
Okay.
Because we don't necessarily have the expertise to grade it if you code it in some language I've never heard about. Okay. Any other questions? No? Okay. So let's start the actual serious business.